Last time we saw the beginnings of how we were going to discuss infinite size. So Cantor adopted the suggestion of Bolzano that one looks at equinumerosity. We'll say that two sets are the same size if they can be put into one-to-one correspondence with each other. So we saw that this was an equivalence relation. And we also saw that Cantor then went on to discover that there were at least two different kinds of infinity. The counting numbers, the natural numbers, omega, and then there was the real numbers, which he showed to have a larger infinite size. So he then generalized that argument and showed that every set X was not in a one-to-one correspondence with its power set. So somehow the power set is a sort of a larger infinite size than the set itself. So what we're going to see today is the Cantor-Schroeder-Bernstein theorem, which says if I've got a one-to-one map from set A into set B, and if I've got a one-to-one map of the reverse from B into A, then there's actually a bijection between A and B. They're equinumerous. So the idea is if somehow as A is smaller than B, shown by the one-to-one map from A into B, and B is smaller than A, or no bigger than A by the one-to-one map going from B back into A, then they are equinumerous. But there's something to prove there, because equinumerous says there has to be a bijection. And where is this bijection going to come from? Well, the Cantor-Bernstein-Schroeder theorem says how to actually construct that bijection from the two injections that are going from A to B and B back into A. After that, we're going to look at the idea of what being countably infinite is. And this will then lead on to our ideas of cardinal arithmetic in later lectures. So we're at definition 411 on page 43. So what we're going to have here is a definition of less than or equals, something being of smaller size. So I take sets X and Y, and we're going to have X is got cardinality less than or equal to Y, right? If there's a one-to-one map. Not necessarily onto. If it was one-to-one and onto, we'd be saying they're equinumerous. But there's an injection from X into Y. And again, we're going to write things like F witnesses that X is injectable into Y. We're going to have it that X is of strictly smaller size than Y. Right? If there's an injection from X into Y, but not the other way around. So I've only got a one-way map. I've got an injection from X into Y, but there's no G going from Y back into X. So if X is bijective with Y, then of course there's an injection from X into Y, and the inverse map trivially shows Y is injectable into X. Right? If F is going in this direction, F functions for this, and its inverse functions for that. Right? So the question is this an equivalence? And as I just said, this is going to be the Cantor-Schroeder-Bernstein theorem. And it precisely says this reverse arrow here. If there's an injection from X into Y, and Y is an injection, there is an injection from Y back into X, then actually they're equinumerous. Now this theorem had a sort of checkered history, actually, and that's why it's got 3 names attached to it. So Schroeder first announced that he had a proof in 1896, right? But then in 98, he published an incorrect proof. Cantor proved it in 1897, but his proof used the axiom of choice, which we'll discuss later, and actually isn't necessary for the theorem. So it's nice to be able to dispense with that axiom. So though Schroeder published a correction, it wasn't until 1911. The first fully satisfactory proof was due to Bernstein, but he didn't publish it. It was published in a book by Borel, but this came out in 1898. So it had a kind of staggered start, this theorem. And it's a little bit intricate, right? So we'll see how the theorem goes. So we're told we've got one-to-one functions f and g going in these directions. And we have g going backwards. And somehow out of these building blocks, we're supposed to find a bijection between them. So we piece together from f and g an h, which is going to be a bijection between an x and y. So it's something like we zigzag backwards and forwards, sort of rather like as if we had mirrors. So let's somewhat fancifully, we'll write out x here and y here. So here's x and here's y. So f is going in this direction and g is going up the page here. Right? So what we're going to do is, okay, g is 1-to-1. If it was onto, we'd be finished. G to the minus 1 would be our h. So the range of g is not all of x. So we're going to define here C0. So C0 will be x minus the range of g. C0 is the bit that stops g from being a bijection. And I've just drawn it small so as to give myself some room over here. So this is x minus the range of g. And then what we're going to do is take this, which I've drawn as an interval, and just going to bounce it backwards and forwards, up and down between these two here. So we'll define Cn plus 1, having defined C0, is we'll apply f to C0. And that's going to give me a collection of things over here, right? So this will be f on C0 is here. And now we'll apply g to that and bounce it back upwards. So then over here, I'm going to call this C1. Right? So I apply g here to go back upwards. So C1 is going to be the range of g applied to the range of f on C0. So again, if you've forgotten what this notation is, look back towards the end of chapter 1. And then I'm going to continue. Here we go. Right. So this here I will be calling, this will be F on C1. And G over here, this will give us C2. And so on. So I just bounce this bad bit backwards and forwards. So now what we're going to do is we can directly write down what our H is going to be. H is going to go in this direction. And there'll be two cases. H of V is going to be F of V if V is in one of these CNs. So it's either in this bad bit or these semi-bad bits over here. Otherwise, if it's not in any of the CNs, we'll apply G to the minus 1 to it. Otherwise. Right, so this will be case 1, and this is case 2. Okay, we should just check to make sure this makes sense right here. Otherwise means for every n, V is not in Cn. In particular, it's not in C0. But if V is not in C0, it means that it's in range of G. So G to the minus 1 of V makes sense. So the definition is okay. So G to the minus 1 of V makes sense if for every n, V is not in Cn. Because then V is not in C0, and that implies that V is in the range of G. And I can define G to the minus 1 because G is 1 to 1. So this then makes sense. Okay. So we have to verify that this H is doing what we want. Right? To make it a little bit easier, let's give a name to these bits, these intervals that are down here. Right? So they're called C's up here. Let's call these ones down here D's. So let's call this D0. And we'll call this one D1, etc. So we'll define Dn to be F on Cn. So Cn plus 1 then is just G applied to Dn. There's nothing there. I'm just using what the definition of Dn is. So we'll check that H does what we want. So it's supposed to be 1 to 1 and on to from X to Y. So we check that H is R bijection. Okay, so H is 1 to 1. It's the first thing to check. So H is defined by these two clauses. Both f and g are one-to-one functions. Suppose I picked two things that I'm going to apply h to, u and v. So the worry is that h of u might end up equaling h of v if it was not one-to-one. That won't happen if u and v, h of u and h of v are defined through the same case. If both u and v are in one of the CNs, we're going to apply f to u and f to v, and f is one-to-one, so that won't send it into the same place. And likewise, if u and v are not in any of the CNs, we'll apply case 2 to them, and g to minus 1 is one-to-one. So again, g to the minus 1 of u is not g to the minus 1 of v. There's only a problem, a potential problem, if u falls under case 1 and v falls under case 2, or the other way around. And then there might be some clash. So we just check that there isn't a clash. So we'll just say that now. So take u and v in x. Both f and g are g to the minus 1 are one-to-one. So the only problem if, say, u falls under case 1 and v under case 2. i.e., h of u is f of u, and h of v is g to the minus 1 of v. And that's the only time, the only way there is going to be some difficulty. Right? But then notice what happens, right? If that's the case, h of u is f of u. So f of u, this is going to be in one of the d's. Because u falls under case 1, u is a member of CM, say. Right? To be in case 1 means the sum m such that v is in CM. Okay, so let's pick that m there. Then h of u is f of u. And this is in dm, which after all is the range of f on CM. That's what dm is here. But now, looking at v now, look at h of v. This is g to the minus 1 of v, right, here. It's not in dm. If it was in dm, then when we apply g to it, right, we would have it in CM plus 1. Right? Sorry, yeah, so g of u yeah, that's right. That's what I've said the right thing. Because otherwise, we'd have g of g to the minus 1 of v here, and this is just v, is in CM plus 1. But V fell under case 2. It wasn't in any of the CMs. So this doesn't happen. Right? So G to the minus 1 of V is not in DM, but F of U is in DM. Okay, so H has sent them to different places. H of U is not H of V. So H is 1 to 1. So we've proved here H is 1 to 1. So now what's left is that it should be onto, right? And then we're done. And when we've done that, we're finished. It's bijection. Okay. Right, by our case 1 here, if I look at any H of E, if it falls under case 1, right here, right, all the D's are the ranges of F on a C. Right? So everything that's in a D is in the range of H. So that's clear. We've got those safely in the range of H. Right? Because for case 1, they're F on a Cn, and that's a Dn. So the union of the M of the DMs, this is contained in the range of H. It's the other stuff in Y that we need to be worried about. So take something that's in Y, but it's not in this union. And we'll worry about that. So Y is, sorry, U is in Y, down there on that bottom shelf. When I look at G of U, it's not in CU, because, sorry, C0, because C0 was X minus the range of G. On the other hand, it's not in any of the other C's either. So G of U is not in any Cn plus 1. Either. This is because Cn plus 1 is G on Dn. And U that we're worried about is not in any of the Dn's. So our U is not in Dn. So U can't end up in, sorry, G of U can't end up in Cn plus 1. Because without it being G of V for something else. For some U that's different from V, and V here is in Dn. I mean, everything in Cn plus 1 is G of something in Dn. So if this guy is in Cn plus 1, it has to be G of V, right? For some V in Dn. U is not in Dn.
But Cn plus 1 is G applied to the things in Dn. So there has to be something in Dn so that G of E ends up being this. But G is 1 to 1. So this cannot happen. So G of U is different from G of E here. So G is not in any Cn plus 1. Hence, for all n, G of U is not in Cn. Therefore, case 2 applies. So, but then case 2 applies. And h of G of U is G to the minus 1 of G of U. And of course, that's just U. So we've proven that U is in the range of H after all. So now we've covered everything. We've covered the things, the U's that are in one of the DMs and a typical U that's not in any of the DMs. So H is on 2. And that finishes that clause and proves the theorem. So that's one way of showing that two sets are bijective. It might be easier to find injections from one to the other and vice versa than to actually demonstrate that there is a bijection. So it is sometimes easier to show that A is bijective with B just by showing the two things, that A is injective into B and B is injective into A, and then appeal to the Counter-Schroeder-Bernstein theorem. Okay. So let's look at definition 413. Again, straightforward definition here. Nothing to do with cardinality. Let X be any set. So we define the characteristic function of X. Characteristic function of any Y, it's a subset of X here, to be the function chi of Y, and it takes X to 2 Remember 2 equals 0, 1. And what chi does is return a 1 if the input is in y and a 0 otherwise. So chi of I of a is 1 or 0 if a is in y and if a is not in y. So this way we identify any subset y of x corresponds to a function from x into 2. And likewise, from a function from x into 2, we can pick out those that get sent to 1, and that gives me a subset of x. So there's a one-to-one correspondence between subsets of x and characteristic functions. Between subsets y contained in x and functions, so we say from x into 2, going from here to here, namely this function chi y. And given any function here from x into 2, I could define some subset of x by a is in yf if and only if f of a equals 1. So this way I've got a map, one-to-one map correspondence between subsets of x and functions into 2, and a function into 2 into subsets of x. So the power set of x is injective into functions from x into 2, and x into 2, any function in here corresponds to an element in this power set. And then by Cantor-Schroeder-Bernstein, actually there is a bijection between them. In fact, I've described pretty much a bijection here. So in terms of size and so on, the power set of x, we can sort of more or less identify it with, and people read this as 2 to the x, although the x kind of comes first up here. So let's move on. Now we'll talk about countability. Say a set X is denumerably infinite. And probably most people just use the alternative and they say countably infinite. If X is bijective with omega. Right, so one-to-one correspondence there. Set is countable if there's a one-to-one map from X into omega. So this actually includes the case when X is finite. Right? So if X is finite, I can biject it with a natural number, which is a subset of omega. So I'm done. So any finite set is countable. Any finite X is countable. So again, let me write what I just said there. Why? Because X finite implies there is an N where X is bijective with N. That's what finite meant. But N is a subset of omega. So there's a map from X to N, but that is also a map from X into omega. Because omega contains N. So any finite set X is countable. If we want to insist that we're talking about an infinite X, then we'll say countably infinite X or denumerably infinite X. So that's the first thing to note. Second thing to note is the next, it's stated as the next lemma. But again, it's straightforward. Sorry, lemma for 415. Any subset of a countable set is countable. Again, no proof required because it's trivial. Okay, check why it's trivial. Check you understand why it's trivial there. So I bring your attention to these exercises. Right, the first one I set here for homework in this week. Suppose I've got a non-empty X here. So being countable is an equivalent way of saying it. If there's a function from omega onto X, sorry, omega, onto. Right? The definition of incountable was that there was a one-to-one map from X into omega. Okay. You need to show that that's equivalent to saying there's a function from omega onto X. Right? So an alternative way of saying X is countable is that there is an onto map from omega onto X, which is what we have here. Right? Okay, so what you have to do then, if you're going from right to left, right here, you've got an onto map and you want to show X is countable. So that means you need a one-to-one map from X into omega. So convert your onto map from omega onto X into a one-to-one map in the reverse direction. That's the hard part here of this lemma, of this exercise. Okay, so then the second part of the lemma here prove that X is countable is countable in infinite if and only if X is countably infinite. Okay, so the words are whirling around here. X is countable and infinite, and X is countably infinite. You'll have to go back to the definitions and check again what these mean. Again, countably infinite meant bijective with omega, right? Countable meant injective into omega, and infinite means not bijective with a natural number. So you've got some equivalence to show here. So 1 is part of the homework, and this is easier than 2. So let's just look at, I'll do 2 then. So let X be countable and infinite. So because it's countable, it's injective into omega. And that is saying not finite. So let G be this one-to-one map from X into omega. Let Y be the range of G. So Y is a subset of omega here. So now I can just define, well, let me say this, Y is a subset of omega. So define then by recursion an enumeration of Y. H of 0 is the least element of Y, using the ordinary ordering of integers, natural numbers. And H of k plus 1 is least element of Y, which is bigger than H of k. Using the standard ordering. Right? I'm just treating Y as a set of natural numbers. And now the point is, we're told X is infinite. Right? So this recursion doesn't stop right here. As X is infinite, for every k, H of k plus 1 is defined. If it stopped being defined at some point, it's because we've run out of elements in Y. We'd only have k elements in Y or something. Right? But that doesn't happen because X is infinite. So H takes omega onto y in a one-to-one fashion. So it's a bijection between omega and y. It's always picking something new. And then g to the minus 1 will take y to x. If I follow that here, this will take here omega one-to-one onto x. So I've demonstrated that omega is bijective with x. But that's just what I need for x to be countably infinite. Countably infinite, bijective with omega. So that proves the direction from left to right. Sorry, out of scope. We assume this, and we prove that x is countably infinite. So that finishes the left to right direction. And here's the right to left direction, which is easy. So this is really just exercises in the definitions. Suppose the right-hand side. Suppose x is countably infinite. So that means, so there is some function f here that takes x bijectively with omega. Then x is not finite, because I could compose bijections and I'd end up with omega being bijective with a natural number if x were finite. X cannot be finite. Okay, you don't have to say this bit, but I think you could say if x were finite, it would be bijective with some n by using some map G. But then I could do G composed with f to the minus 1, and that would take omega bijectively with a natural number. We've already got one of our earlier corollaries here that says, well, that says that omega is not infinite. I think we even said that, corollary 4.8. So x cannot be finite. Right? So what we have then is x is countable and then infinite. Countable because it's injective into omega and it's not finite. Which is the left-hand side, which is the left-hand side up here. We went from countably infinite to countable and infinite. So this finishes the exercise there. Fine. There'll be more on countability and various bijections and injective functions again next time. Okay, fine. Have a good week.